What's the challenge with in team one?
Well, I don't know. I
Ah,
think that some of them started already doing the task, but
okay.
I don't know like if we are going to do it.
I think you are doing it. I mean, I think you guys have decided to do it singly, so you can do it singly. You can also decide to do it as a group, so
Okay.
it's all allowed.
And for me, I have a concern regarding the reads when
Okay.
downloading the reads. Like when I download some of them, I have like some of the files which have 96 like megabyte. Is it enough for sequencing rate?
96 megabytes.
Yes,
I say
something like that.
it's like
96 or 100.
yeah,
Yeah.
it's microbial, so it could be because uh it depends on the technology anyways, but the genome of microbes sometimes is not up to, it's about 5 megabytes. The genome, the complete genome, just the genome, no quality rates, no quality score, nothing, just faster file of the genomes is sometimes around 4.85 megabytes. So if you have uh if you have 90 megabyte, right?
Yeah.
It's okay, yeah, still okay.
And like, do I have to download the reads from one project, like,
No.
or different project?
Just ensure that you have different countries.
Okay. Yeah.
I mean, it's maybe, I mean, some people can do experiments in, say, Kenya, and others in Canada, different
Yes.
experiments at different places. So we just want to be able to know the antimicrobial resistance gene, the prevalence of resistance genes within specific countries. I think someone already did something very interesting, and I saw the report, and it's so interesting that there are some things that are not found in Nigeria and some are found in, say, Canada, for example.
So, like, I did this actually, but my question is like when I use the accession number, I don't know if it's correct. Like, for example, I want to search for uh, like sequencing data from Senegal. If I uh, write the name of the bacteria on the search box and I hit enter, it will
Mm-hmm.
give me results, different results.
Mm-hmm.
So when I use the SRP something like that, it will give me a bunch of sequencing reads. So do I like download those reads or
I think
just
you
select?
just pick a few. I mean,
Okay.
pick the ones that are enough, and you can complete before Wednesday, because we just concluded that Wednesday should be the last day.
Yeah.
Remember, we shifted stage 2 until Wednesday last week. So so try to do something. I mean, within a project, you can just select 5. Within a project, you already know uh, these samples are from the same country, are from the same author. So you can just prioritize 5 from that project, move to another project, prioritize, select another 5. I mean, just continue to pick randomly that way. It's not exactly, it's not as if you want to publish it at the end of the day. You might decide to work on it on a larger scale and publish it, fine, it's okay. But just for the sake of the project, with Akbai, just try to do something around 20 sequences. You can
Okay.
pick, yeah, just pick any 5 from that one that produced so many reads, pick 5. Look for another one that is producing so many reads from another country, and pick 5 again. Just continue to pick 5 randomly, and
Yeah.
you will be done in no time.
Thank you.
You're welcome. Yeah. Yeah. Any other question from project 1? Okay. Then, did I answer your question, Francois?
Yes. Yes. Yes.
Okay. Stage 2, I mean, sorry, project in 2. Is anybody from project team 2? I think it's project team 2 I plan to discuss with today. I don't know why they are absent. It's true. Nobody's from project team 2. Okay, we'll go to project team 3. Anybody from project team 3?
Yes, good evening.
Yeah, good evening.
Yeah, in project team 3, we're having issues with the linear disequilibrium analysis.
Linkage disequilibrium. Okay.
Sorry, leakage distribution analysis.
Yeah, so I looked at the data, that's true. I looked at the data and I realized there was I think there was a mix-up in the origin of the data.
Okay.
But, still, you guys will have to work on something. So
we can't do it.
No, of course you would have to do it anyways, but typically the data is actually atypical as it is, but because it lacks information on the phenotypes. Now, the thing is, the data set is from, I think did you guys do it to the PCA stage?
Yes, we did the PCA stage.
Now
the LD is like the last stage.
Yeah. So when you did the PCA thing, you realize that there are 4 major populations.
Yes. Yeah. So there were 4. There was one. Yeah, there were 4 populations.
Can you share your screen? Do you have?
Okay, let me open my arm.
Guys from group 1 and 2, we are kind of done, but if you guys still have questions, you can wait. Group 3 stage, project 3 is going to take some time, I can assure you, but it's a much more complex data set.
Let me just, I don't know, my R is not opening.
Okay, maybe I should share from my end what I have here.
Let me, you said?
Can I share from my end, or you guys should come, or you?
Oh, you can, let me keep trying to open mine.
Okay.
Because my R studio is not opening.
Okay. Is anyone talking from group 3 that can share their screen?
Yes, I am, but can you hear me?
Yeah.
I'm working, I'm calling from my phone, but let me try and connect to my device.
Okay, we can wait then.
Yeah, this is cool.
So next time you guys can always prepare with your PC.
Yeah, I thought it was better.
Yeah, let me try to. Okay, I have to probably log in. Don't mind me, I have multiple ways of accessing the server, so don't worry.
Or do you want me to share just the server or the?
No, RStudio. I'm logging into RStudio, yeah.
Okay.
Yeah. It's RStudio server. Okay. So you guys probably did this already, yeah?
Yes.
I see. Cool. So after doing this, you have some other steps in the, let me check, yeah, so you have to create a prune set of markers. I guess you guys did this already.
Yes, we were able to do all this till the last stage. So we did the,
did ethnicity by distance. you did multi-dimensional scaling. And you will notice that when you perform the multi-dimensional scaling, the result of this MDS is the same as the PC, kind of. If you look at it very well. Did you notice that?
Mm-mm.
So
We
the
did.
result of, I have the terminal here that I can. Let's clear. This is the result of my MDS. If you guys, you notice that it ends with .mds.
Yes.
You can try to share. Can you see my screen very well?
Yes.
Okay.
Yes.
So you can plot this C1, cluster 1 against cluster 2, and you will realize you have something similar like this. So what I'm trying to say now is that these steps are still like a replication of what happened in PC. But when you did this step, this pruning of markers, so with this step, you have reduced the number of total SNPs, that is total variants that you have marked, that you are screening for. So in essence, you are looking for something that is, you are looking for genes that correlate with individual population, but do not, for example, where is it? Where's my plot? Okay, you have this CDX. Let me try to change the color by, let's see if we can change. I don't know where I did the plot. Okay. Population name. Let's change it to name. Okay. Yeah, so you have the Chinese. You have the Chinese, you have the un-Chinese, you have the, and that's why they didn't, and they look alike anyways. You have the Vietnamese and whatever I say, you have it. So, sorry, I'll just close my door. There's a lot of noise around here. So what you are trying to do now is you are trying to look for the SNPs, the minimum set of SNPs, that is variants, that are unique to these guys, but are not found in these guys and others generally. What makes them unique? What makes these green guys unique, these Vietnamese unique and different from the Chinese people? Generally, this data set is in itself from their HLE variants. I think I mentioned that, yeah, human leukocyte antibodies. So what you are trying to do in essence is that you are trying to look for what makes, sorry, who's on the call? What are the names? What are the names on the call? I just want to use you guys as an example. What makes Orelua different from, from me, for example? We know we are both human beings. We are both, for example, let's say we are both from Lagos State. We are both Yoruba people. We are both Nigerians. But what makes us, what are the set of, I mean, we are up to 90% similar, but what are the sets of genes that are different between the two of us, that makes us different, that makes us unique as, okay, this is Orelua and this is Kwali. Yeah, what makes us different from each other? So that's what you are trying to do from this multidimensional scaling. And when you do the multidimensional scaling, you probably have this kind of thing again. Now, the next thing is, remember that before you did this multidimensional whatever, you did this pruning. So you try to remove some of the things that are consistent across board. That's what you did in the pruning stage. Like the remaining 90% that are similar to all of us, you removed it. So what you cannot do is to rank those things. But because I guess we did not mention it in this notes, so in the tutorial, you will notice that no, here, you would notice that they did, examine the new SNPs just after their identity by descent stage. What they did was they wanted to merge an extra data set, but we don't have any extra data set to merge with here. So we are just working on the original data set we have. So instead of merging, we did, so you could just do the direct, what do you call it? You can do the direct association tests. So they call it genome-wide association studies. So what you are doing is to actually test for within the data set and identify the SNPs that are unique to each phenotype. And in this case, the phenotypes are these Dai Chinese, and Chinese, Vietnamese. So in some other cases, the phenotypes could be, for example, a disease, a particular disease, maybe diabetes versus non-diabetic, cancer versus non-cancer. So this could be the phenotypes. So what you're now trying to do, in essence now, what you should try to do is to, first of all, after your identity by descent, you should do this association test. But because there was the data so the data you have does not have, so the data you have is a complete data, but it does not have, within the bed file, it does not have information for these phenotypes. Like, okay, there are different human beings, but you don't have the information for the phenotypes. You don't have the information for their, say this is Dai Chinese, this is Han Chinese. You don't have that within the data set we give you. We only created this externally because we know the source. So we can merge it from the source, and the source is 1,000 genomes. So because of that, we are unable to perform this association test. But what you could now do is, we are going to skip this association test because we don't have that information of phenotypes within the data set itself. So the next thing that we could do is to now perform linkage disequilibrium itself directly here. But for linkage disequilibrium, you need to know the genes beforehand, So unfortunately, we don't know any gene beforehand. We don't know the SNPs, that is the single nucleotide polymorphisms, beforehand. We don't know which of them to select. And if you look at your prune data, let's see. Sorry for shrinking your plots this way. Well, this is the prune data. These are the ones that will go in. So we say, I can just say less. So these are the SNPs themselves. And if I try to count the number of SNPs that are here, you see that they are, you see that there's about 20,000 SNPs. That's a lot. It's a whole lot. You can decide to make a heat map for them, but let's hold on for now. But what you can do is, what I did, let me tell you what I did. So in the identity by descent stage, I increased this threshold. No, not the identity, but in the pruning stage. Yeah. So this, because at this pruning stage, it's already going to create a set of genes that are suitable for linkage disequilibrium. Okay. So I increase this to 100. You can even leave this as 50. You can leave this as 10. You can even increase this. Or no, rather, to be more strict, you have to reduce this to maybe 5. And then you reduce this more. You are reducing the correlation. So you are removing SNP that has R squared greater than 0.2. Because if they are close to each other and the correlation is high, then that means they are located on the same gene, and it's not exactly genome-wide association. It's just gene-wide. It's not genome-wide. You get it? So we are trying to increase the search space. So you can increase this to say 100. You can leave this as 10 if you wish. You can leave this to 1,000 if you want. And you can further reduce this to maybe 0.05. And yeah, so I reduced it, and then I have, I think, hold on, I have to check. Okay, I think I have it here, but initially, I think it was about 50 something thousand, initially 50 something thousand. And then I reduced it to 20,000, as you can see here. But still, this is still a lot. So what you guys can do is to so what I did is I looked at these guys here, I mean the guys here, and I selected only chromosome 1. It's a lot of try and error. You can decide to work on each of the chromosomes one after the other to look for the genes that are and the SNPs that are in high disequilibrium. But another thing you can even do from here already is that you can look at these guys. Sorry, let's. Yeah, you can even already from here, let's try to copy this guy. I can go to, there is something they call DBSNP. Yeah. That's the database for SNP. It's also on NCBI, so it's for all the SNPs, and you can just copy and paste it and search it here. So normally you should have something they call RSID, but because the data set has been, I don't know, I didn't expect the data set to be that messy. But yeah, the data set has some internal problem, like it's not well annotated, but this is the SNP, and you can already begin to see some information. So I think it's more in Europeans than Africans. So I don't know what to say about this because it's supposed to be Asian, and in Asians there is little reference to it. And you can now look at the clinical significance. I don't know. The clinical significance is, yeah, I don't think there's any major clinical significance associated with these variants. No track data found in this range. Okay, so there is really no significance for this particular variant. It's just, so there are some variants that nothing, they don't really have any consequence. And this is ClinVar data. And the ClinVar is like the highest of the highest in terms of clinical genomics. So so you have 20,000. Instead of starting for the old 20,000, you can now do the linkage disequilibrium thing with the, let's say chromosome 1. Let's pick chromosome 1. So we have so many things in chromosome 1. It's actually a lot. It's actually a lot. Okay, this is where chromosome 1 stops. But there is a way, if you look at your tutorial again, it's a lot of back and forth. Sorry, guys. Your work is probably the most difficult. It's a lot of back and forth. But there is a step, there is a way to extract the genes in chromosome 1. So you can use this SNP method, but because we don't have this RSID information, there is another way to extract everything in chromosome 1. And I think I have it here. Yeah, from here. Plink B file, that's your asia.ped or asia, whatever you have. You have chromosome, you select 1. Then from, you can say, so since you have, okay, I've reached the mark, sorry. Since you have 15,274, but then remember this is KB, so you have to divide that by 1,000. So you now have 15 here, you have 15 here, and for the next one you have, hold on, for the end, you have 1, 2, whatever, and then you divide it also by 1,000. You put it here as well. And then it creates a miniaturized data set for chromosome 1 alone. And you can now put that here. So I can quickly do that, you know, it's a simple thing. It's not so complicated. Paste. So Plink, so our data is Asia, but I want chromosome 1. Hold on, I'll just switch to terminal 2. Yes. CD, RD. I just want to be able to see. So we said 15 here. We said 15 for the first part. So because it's human data, it's always very complex. Human data is naturally complex. Human beings are complex themselves. So I have prompt. Okay, I'll just leave the files. Oh, sorry, which I'm still outside. Okay. I have pruned markers. And then I'm trying to look for the last one, just to focus on, just to zoom in on chromosome 1. So you have, I mean, you can do this programmatically if you can. You have 2, 4, 9. I'll copy that and I'll go to terminal 1. And I'll delete 3, 1, 2, 3. And then I would say, yeah, so I would say, I think I have to also specify the output. Let's see, yeah, I think I have to specify make bed. Hold on. Yeah, make bed. Yeah, so it's done now, and it has saved everything as Plink. I didn't specify an output. I should use double hyphen out, but I can always rename these guys back myself if I want. I can now rename them Plink. Oh, sorry. Plink bed. I'll move it as Asia C1.bed. And then I'll say Plink.beam to Asia, and let's go C1. No, beam this time around. And I'll move the third one. So they have to have the same initials. Plink.farm, and I will say Asia, let's go C1. Yeah, so I have them here, Asia. Yeah, and then I can now perform my linkage disequilibrium experiments using, yeah, hold on, where is it? Yeah, I can perform my linkage disequilibrium experiments using these guys. Yeah, using them. This is in the initial step we did just now, but we don't have the RSID, so we use the information on the genomic coordinates of the SNPs. So here, what you can now do is to perform the linkage disequilibrium step using this R-square equation. I mean, R-square code. And to do that, you say Plink B5, and you use, hold on. What did I name it again? Oh, sorry. B5 Asia, and let's go C1. Okay. Then you name it R-square. I mean R-square. And I think the output, you can specify it as Asia So Asia C1, and we can run it. Let's see. Yeah, so it's done. And the report is sent to Asia C1.ld. I'll clear again. And I'll see Asia, Asia C1. .ld. There are so many L's. Okay, that's correct this time. Yeah, so what you notice is that there are a lot of this is now your final output, linkage disequilibrium output. This is the SNP-A versus SNP-B. So you are comparing this guy, in this case, with this guy, and seeing if there is an association between this SNP, this mutation, if you like, and this mutation. And the correlation is low. In this case, we have 0.2, but you can immediately begin to focus on things that have this 1, for example. And we can decide to look at it already on our RSID. I'll just go back. Yeah, when I'll paste it here, I'll see, let's see. So, it said it's related to North Sweden. Okay, we can look at it much more. Am I too fast, guys? Yeah, so another thing with the DBSNP is that European and American data are the highest. So you might not find much, but yeah, I think they found some in South Asian population already. And that's really cool because we are looking at Southeast Asia. So we can zoom in on this. And yeah, so you just have to look for the genes that are, so your job is not to essentially begin to find the significance of all the mutations, but your job is just to locate and tell us specifically which genes are in high correlation with each other. For example, this is 1-to-1, and that's really strange if it has not been discovered before now. You have a lot of 0.8. So you remember one rule of thumb in linkage disequilibrium and genome-wide association studies generally is that association does not mean causation. So the fact that they are associated may not really mean that it's the cause for the difference in these populations, but it's a potential candidate for study, generally. So that should be your conclusion. You are not saying this is the reason why Asian and Chinese people are different from Vietnamese people. No, you cannot say that. At best, what you can say is you suggest, or you are proposing, or you found this to be associated with the difference in the Chinese versus Vietnamese HLA population, HLA allele or HLA gene. But you are not saying this is the reason, this is the almighty cause of the difference between Chinese and Vietnamese people. You guys were quiet all through. Nobody asked any question.
So we shouldn't look at it in terms of clusters anymore, rather focus on the chromosome.
You said you shouldn't focus on what?
Because the question that was asked was that we're supposed to look at it based on the cluster 1, thereabouts, the first cluster.
Okay. Yeah, you can't do that anymore because we don't have, because we don't have, sorry about that. I got distracted. Because we don't have the phenotype data. It's the phenotype data that will create the clusters. So when you now have phenotype for, say, Chinese people, you can now focus on let's see. Sorry, I really got distracted. You can now focus on the mutations in this particular cluster rather than the entire cluster rather than the entire 4 populations. But in this case now, you just have to be descriptive. You just have to be descriptive. Yeah. So it's not, you can't be very specific anymore, because you don't even know, how will I say? You can't really say, because now you are comparing 4. You are no longer comparing one cluster against the rest. So it's difficult now to say this one is the reason for the entire 4. If you are comparing one against the rest, it will be easy to say, okay, at this point in this cluster set, this is where this single gene or this single mutation can affect the 4 populations. I mean, can affect the rest of the other population. But in this case, you now have 4. And it's quite much more complicated. Once you exceed 2, it's more complicated. I'm sorry for the data set it's not so clear. It's quite confusing. And I think this is the best we can do on this data set for now. If we are able to, because the data, some of the, so what you need to know is that it is human data. It's very difficult to get to the roots and the complete metadata. They are not going to release everything. So it's normal if you face these kind of challenges, except it's a project that you are funding by yourself and your laboratory is the one in charge of everything. It might be difficult to get the complete metadata. Did I do well in confusing you guys more, or? Your voice was mute, sorry.
Yes.
I confused you guys more.
A little bit, but I think what should we do again?
Yeah, so what you cannot do now is to just, maybe someone can focus on chromosome 1 and find the RSIDs that are different there. And you can just also use this DBSNP to be a little bit more descriptive and show that it has been discovered previously, but maybe in, say, goodness, get something again. Sorry, please, I'll get back to you guys. I'm coming. I'll just stop sharing. What I'm saying is, so what I'm saying is, you guys might have to focus on, I mean, you can just distribute the chromosomes amongst yourself. Someone will pick chromosome 1, another person chromosome 2, another person chromosome X, if you wish, and then you try to find the linkage disequilibrium. I think I can also advise that maybe you guys should focus on chromosome 8, because some previous studies already showed that chromosome 8 is very important for that data set. So you guys can also work on chromosome 8.
Okay.
Team is projecting 2 here. Okay. Out of projecting 4.
Hello, William.
Hello.
Yeah, I'm here from project 4.
Yeah. Can you?
Yes, so I have been able to download the eigenval and the eigenvec files. That's where I'm at now. The RStudio, I have no idea what to do.
And did you try to reach out to Ankita, or?
Yes, I have actually. We're supposed to. We're going to meet to finish it up.
Okay. I mean, what remains?
So she knows what to do.
Yeah, and you can also use Excel to plot it if you want. If you know how to use it. It's just plot one column against another. you don't have complex problems like project 2. Project 2 is really complex. I mean, project 3 rather. I really pity them myself.
I was going to choose that project 3 at first. Thank God I didn't choose it.
No, if you're interested in precision medicine, you might, I mean, it's a really good project to work on.
Yes.
Because you have granular information about individuals. But it's very difficult to get such kind of information. That's why the data set is whatever it is right now.
Okay. So for our own projects, what are we plotting against each other?
You are plotting a principal component against another. So you are plotting high level of variations. So what you have in principal component 1 is the information, is an abstract information that you don't know. And that is what project 3 is trying to investigate. But what you are doing in project 2, in project 3 is just to actually see the abstract level of an abstract, how would I put it? Something you don't really know. I mean, 2 things that you don't know, those are principal components 1 and 2. But these 2 things are in a way descriptive of the entire data set. They can describe the variation in the data set.
Is it the SNPs that we are plotting against each other?
Yeah, you are not exactly plotting the SNPs. You are plotting properties of the SNPs.
I don't understand.
How will I say this? Okay, as a person, you have certain properties. You have, you have a tall, or maybe you have a height, you have a length, you have a geographical location, you have name it, different things. I myself also, I have different set of information.
Yes.
If you compare C to T, I mean, if there's a mutation in C that change to T in U, and if there's an information that changed from C to T in me, will you be able to tell the difference? If you are just write C, I mean, let me try to share a whiteboard. If you have C, for example, to T, I mean, so these are, you know, C is a nucleotide and T is a nucleotide. This is Eniola, right?
Yes.
And I will say this is Wale. So you have C to T. So imagine you don't have this. Imagine you don't have this. Will you be able to tell the difference between the two?
No.
Okay. Well, if I put my name here, if I begin to put things like,
so is it different ancestries we are plotting?
No, you are not looking at ancestries. You are not looking at ancestries. You're only looking at the properties of these SNPs that make them unique to say, what populations are you looking at?
So we're looking at 4 different continents.
Yeah. So you are looking at, so what makes this C to T specific for, say, Asians,
Africans, Asians, Americans.
What makes it specific? And what makes this one Asian, and what makes this one African? That's what you are trying to plot out in the plots. And when you make the plots, you will realize that maybe there is a cluster here, there's another cluster here, there's another cluster here, and there's another cluster here. It's because of so they call it dimension reduction, reduction of dimensionality. Because these SNPs have multiple things, multiple features, and those features are called dimensions. It's just some nonsense mathematics. Don't bother yourself about it for now. So they have multiple dimensions. This is a dimension. This is another dimension.
So how do we make sense of the?
Do you have audio? Can you hear me?
Yes, I can hear you.
Okay. Temitope, you can try to look at your audio better. Yeah.
Okay. Maybe you can try to log in and log out.
Okay. No, log out and log in. No, log in and log out. She's already logged in. Okay, so you have the properties for this guy, you have the properties for another data set. So what you are trying to see is you are just providing a high-level overview of the distinctions between these populations, that they are indeed different from each other. That's one. You can't really see at that level what makes this population different from this population. And that is what the project we just finished discussing. That's, I think, project 3. That is what they are discussing. That is what they are doing. Yeah, like I said, what you are trying to see, you are not investigating the reason why you are not really investigating why this population is different from this population. You are only trying to see you're only trying to visualize
how different they are.
Yeah, and see for a fact that this population is different from this population. And I mean, for example, at the end of the day, the kind of SNPs that characterize this population, say Asians and Americans, I don't know I can't remember the continents again, but say Asians and Americans, it's also trying to inform us that, see, if you develop a drug for Asians, there's every possibility that it might not work for Americans, because intrinsically, for example, if okay, you guys worked on chromosome 1, you guys are working on chromosome 1, I can remember that. Yes. And you are developing a drug that targets a gene produced on chromosome 1. And say, for example, it's just everything I'm saying now is hypothetical, but say, for example, the chromosome 1 is, I mean, yeah, you are developing a drug that targets this chromosome 1, that targets a gene located on chromosome 1, and this gene has some mutations, for example. Now, let's say these mutations are now continent specific and is part of what contributes to this general population. Now, you can now begin to see that if such a drug is developed and it works for Asians, there's a tendency that it will not work for Americans, because there is a mutation that is significant enough to even distinguish Asians from Americans. Like I said again, it's not entirely, sorry, can she hear us? Temitope, can you hear us?
I don't think she can.
Because she's still asking the questions and I'm trying to answer. But hopefully, maybe she can watch the record. I hope I'm recording it. Yeah, I think I'm recording. So the important thing to note is that you are not trying to say this is
okay. These SNPs are present in this particular population.
No, you're not saying what you're saying for now.
Okay.
You can say that if you have more information on the phenotypes, like what they are doing in project 3. But in this case, what you are trying to say is just to show and provide proof of concept that indeed the genomes amongst the global populations are different from each other. And it's more like you are building a case for more, what do you call it? For more diversity in genome projects.
Yeah.
So that's the essence of this project. It's not, you are not exactly going to say, oh, I've discovered it.
Me, I actually thought we were going to look at the SNPs that are different in different populations.
If you want to, you can, but it's going to take, it takes a long time. Even the one we thought we pre-processed already for stage 3, group 3, it's it's a little bit more complicated. They have to look at all the chromosomes now and see where the mutations are really happening and see which mutation is correlating with what. You see, it's not so direct, and you might have to do a lot of investigations.
Okay, another question. So for these principal components that we are plotting against each other, is it automatic, or we're the ones that will choose what we are plotting against what?
Yeah, so usually in principal components, you are going to get something like a rank of the principal components, and usually principal component 1 is the highest.
I think that's in the eigenval file, right?
Yeah, I think eigenvalues, yeah, you have them there. Yeah. And then in principal component 2 follows, then down like that to whatever principal components is stopped. So with principal components 1 and 2, that's what it's principal components 1 and 2 are usually enough. But because of, they call it the cost of dimensionality in biological data sets. So it's like a course, and the biological, anything can just happen. One single thing can just change the course of events in nature. There might be a volcano that has happened sometimes, and maybe it caused the beginning of some set of human beings, and you can only locate it in principal component C5. So it might be worth trying to plot principal component 1 against principal component 5. You see? It's just, so this principal component, just consider them as abstract things that determine how these populations vary from one another. It's a little bit still complex. You probably need a little bit. You need a little bit of statistics, yeah. But you can go to I would say
these principal components, they don't have any name.
Yeah, that's it. That's why it is abstract.
They're just abstract values.
Exactly. That's it. You can't really call them anything that's okay. Maybe this is related to height, or this is related to color or whatever. No, it's just abstract like that. It's just principal component like that.
Okay.
Yeah, sorry. Okay, I would stop. How do I stop this thing? Yeah. Any other comments or questions? Okay, I think we have group 5, project 5. Is it project 5 or let me be sure? Okay, there's nobody in project 6. Everybody is phylogenetic in 6Y. Project 5, any question?
Hi, I'm in project 5.
Okay. Yeah, I think we were chatting about, do you have any questions?
Yes, about your suggestion, actually. The variance calling pipeline, can it work on just one data set, like one forward and reverse data set without more?
Sorry, you said the what pipeline?
The variance calling pipeline.
Yeah.
Can the input data just be for a normal data with only one forward and one reverse, no tumor sets?
No tumor cells. By tumor, you mean?
Like, for the stage 2, we had normal and tumor, and then the reference genome. And you said I should test it on the stage 1 data set, and that one was just.
Yeah. So the data set should not, it's not necessarily, I mean, your pipeline should not necessarily be, how will I put it? So there are multiple cases. I mean, you can be comparing, there are multiple diseases. It doesn't have to be tumor or normal. No.
Okay.
Well, how will I put it? You just have to be able to input the pair of forward and reverse at the same time. That's all.
Okay, and I can compare that the stage 1 data with the reference genome.
So if you want to compare the stage 1 data with the human reference genome, it's like you are comparing. It's like you are comparing human being to. It's not even microorganism now. You are comparing human being to virus, because the data set in the stage 1 is really small. Yeah, but you can. Okay, you want your reference genome to be inbuilt already in your pipeline.
Not necessarily. The way I did it, I made it that when it gets to the reference genome part, you can actually input the link to download.
Okay. Okay, that's quite smart. That's quite smart. Yeah, that's quite smart. You can. You can. I look forward to seeing your final pipeline.
Yeah, me too.
Yeah,
Thanks.
Quite smart. So you can decide to put the link. I look forward to seeing it. I look forward to seeing it. I mean, I'm optimistic. I can already see your line of thoughts. Okay, and that's really smart.
All right, I'll try it, and if I have any issues, I'll send it on the channel.
Sure. By the ways, the workshop closes on Wednesday. I will make an official post about that anyways. But the workshop closes on Wednesday. And we encourage you guys to try and complete what you are doing. For certification, you have to complete your projects, at least, and all the tasks, sorry, not just the projects. Stage 1 to 5. I mean, stage 0 to stage 3, because stage 3 is 2 weeks. And yeah, so you have to have like 3 projects, 3 tasks, and 1 project. But I think nearly everybody has that already. It's just the projects that is, I mean, it's important that you do everything. It's that way we can be able to confirm that you really, completed it. And so someone is asking me if there will be access to the library. Yeah, sure. But not on ArcBio's platform. So the platform might still exist for you guys, okay? Because we might delete it. It's like a CD, so we play it, and once you are done watching the movie, we remove it. So yeah, it will still be available, but then you still have we have another database to share with you guys, and you can directly access it from there if you want. So you really don't have to rely on what we share from now. I mean, the current status of it as it is. And it's more curated and clearly, step by step for you guys. Any other question? Yeah, you can still make submissions until Wednesday. Try to complete everything before Wednesday. I don't know, not even Wednesday, I think even till the end of the week. But officially, you might not be able to receive mentorship and all after Wednesday. But if you write to me in secret, I will respond to you, don't worry. Any other question? There's no stage group 6. So I look forward to seeing your final reports. We already have 2 reports already. At least 2 people have submitted, and that's quite interesting. So see you guys tomorrow, hopefully. If you need another project meeting, especially, so now it might be, I'm not sure if it will make a lot of sense to be talking about everybody's teams, but if you need immediate response or immediate discussion on your team's project, just hit me up and we can start discussing. Okay, guys, have a nice evening and see you guys tomorrow. Bye.